So now I get to do module 5. Thank you, Ian. Thank you, Kate. All right, let's do it. Let's get going with module 5. So this is part 2 of like thinking about analyses. And the goal of this part is to get us all the way to AIM type 3. AIM type 3 is comparing adaptive interventions. So let's get going. You guys ready? All right, so the third, we're going to define the third common aim. We're going to hopefully give you some language, take or leave, you know, like we like to do. We're going to explain some key stats considerations, and then we're going to teach you how to interpret results, you know? So same thing we did in the last module, but the last module you already knew how to do it. This one might be new things, potentially new ideas that you haven't seen before, and new stats methods. But remember, this is not like alphas, betas. This is me just trying to, or us just trying to deliver the basic intuition so you're able to write a cogent stats analysis section. And even if you're not the quant person, you should be able to write the cogent stats analysis section, I'm sorry to say. You have to be able to understand everything that's being said. Otherwise, you know, you got to be able to. Okay, so you all know about the Pelham Smart ADHD Smart. You all know about the 4 embedded AIs. So just so you know where we're going into the world in which, Danny, I want to compare these 4 things. That's where we're going. We haven't done that yet. We haven't shown you how to think that through, how to compare these 4 adaptive interventions. And by now you know that they're in there. They're in the study. Okay? All right, so let's get right to it. The first, and this is going to be broken off into little pieces. I think you all education people call it scaffolding. We try breaking it off into little scaffolds. So we're going to do this one first, then this one, and this one is going to be estimating the mean outcome, school performance, under one, you know, each, but under one of the embedded adaptive interventions. Once you know how to do it for one, you know how to do it for all 4. And then we're going to shift. That's the stairs that you're going to stand on. And when you get here, we're then going to move to estimate and compare the mean outcome under 2 of the embedded adaptive interventions. Effectively, where we're headed is, first we're going to show you how to get the mean school performance under one of them, and then we're going to show you how to do it all in one fell swoop. It's kind of cool, actually. You're going to love it. I think you are. All right, so just imagine for a moment that your primary aim is to compare these 2 adaptive interventions. I just chose these 2 as examples, okay? Nothing I'm going to say is specific to these 2. You could have chosen a different 2. All right, how many pairwise comparisons do we have in this study? There's 4 adaptive interventions. 1, 2, 3, 4. How many? 6. Yeah, can you answer? 6. There's 6 pairwise comparisons, right? So you have to hang your hat somewhere. if you know, to follow along here, hang your hat on any 2 you'd like. These are the 2 that I'm hanging my hat on, just to illustrate. Everybody with me? So this is where we're going to be going eventually. But before we're able to do that, you know, well, first let's talk about language. How do we formulate this? These are a little harder to describe in grants because an adaptive intervention is it's a slightly more complex thing than saying, start with BMOD, start with MED, right? So the languaging gets a little trickier, but trust me when I tell you, we've done it. There's ways to do it. So here is like the long version. To investigate whether an adaptive intervention that recommends start with BMOD if you're not responder augment, else continue, is better than an adaptive intervention that recommends start with MED if you're not responder augment, else continue, in terms of school performance. That's a mouthful, right? It's like, this thing is going on and on. But there's other ways to say this, and I don't even know if I put them up here. You ready? If you think about like the 2 adaptive interventions here, they are identical, except for one starts with BMOD and one starts with MED, right? So there's other ways to language this. You don't have to use this, and I don't have the words up there, but I've described it in the past like, dear reviewer. You know, imagine a world where non-responders get augmented, they get both, BMOD and MED, and where responders stay the course. Just imagine that world. All I want to do is compare 2 versions of those, one that starts with BMOD and one that starts with MED, right? You can language it however you want, but that's what's going on here. Everybody see that? Okay, and then there's yet other ways to do it more efficiently. All right, so in red, I have the start with MED If it ain't broke, don't fix it. Augment if you're not responding. And in blue, I have start with BMod. If it ain't broke, don't fix it. Augment if you're not responding. So I'm going to kind of use that comparison all the way through. What's cool here, and you're already seeing it. Remember how we talked earlier about like using those letters A through F to describe? If you even think your reviewer is confused about the language you use, whatever it was, use the boxes. The adaptive intervention consistent with boxes A plus B versus the adaptive intervention consistent with the boxes D plus E. That's one way to do it. I think that's one way Greg did it when they wrote their grant, right? And there's other ways too, you know? Use these graphs to your advantage. Use the little boxes. This is helpful. In fact, in every single grant I've ever written that has used ASmart, I have had a table with as many rows as there are embedded adaptive interventions. And then in the columns, you'll have stage 1, response, non-response. Stage 2, right? These are all columns. And the last column is which boxes. You can picture that table, right? That's a very useful tool. Yeah? Can you picture it? Okay, great. So we're going to be comparing boxes A plus B versus the mean in boxes D plus E. That's what we're going to be doing. We're going to be talking about like the stats about that. And let me ask you, well, you already saw the answer. You can't just willy-nilly take everybody who ended up in these two boxes, all right? Take all of them, right? Because these are all kids that ended here and kids that ended here, right? They're unique kids, right? That ended here and unique kids that ended. Take all of them, put them all in one bucket, and say, what was their mean school performance? Why do you guys think we can't do that? Why would that be unfair? Anybody got any thoughts? Not my students and not my postdoc. Anybody have any thoughts why that wouldn't quite work out so well? Anybody have any gut feelings, gut thoughts? It's okay if you don't know the answer. Just take a guess. Why wouldn't that be a good idea? The answer is basically because by design, there's half as many non-responders in box B as there should have been. Because I decided to randomize the non-responders. So that's what we're going to be talking about, is how to undo that thing that thing I created, that monster I created. How do I now backtrack? Because it's not fair if I just take the mean school performance in those boxes. Everybody with me? And it turns out backtracking is not that hard. You'll see why. All right, why not? So why not? Well, imagine Lewis. All right, so these is two imaginary people. Imagine Lewis, all right? And Lewis had a half of chance of getting med. And you don't control it. Lewis just happened to be a responder. Okay? So we put Lewis in there. All right? Lewis ended up in box A. All right, now imagine Noor. I love that name. Noor. Noor also had a half chance of getting med. You had nothing to do with it, right? But Noor ended up being a non-responder, and Noor ended up being here. So what happened? Noor did not respond, so it's kind of like I chopped Noor in half. Right? Think figuratively, right? Like I chopped Noor in half. That's not actually what happened, but it's kind of like figuratively. If you think of all possible Noors that ended up here, I chopped them in half. Well, that's not fair, right? I have like people in this box that are all half people, you know what I mean? And I have people in this box that are full people. That's not fair, right? You guys with me? The good part is I actually know that I cut them exactly in half because I'm the one that chose the coin flip, right? And had you chosen of 30% or 70%, well, then you would have cut them a little bigger and a little smaller, right? Everybody with me? So that's going to work to our advantage. Are you guys following me so far? Yeah? So that's why there's imbalance. It's not fair. Noor is only representing half themselves. That's not fair. All right? And here I am saying it. Lewis had a half times 1 chance of following AI1 because there was no randomization here. So what I teach my PhD students is like, just follow the probabilities and multiply them. Half times, oh, that's it, half. That was Lewis. And then, half times half. Oh, that's NOR. That's a quarter. Quarter chance, right? You guys see the intuition? All you need is intuition right now. That's all I want you to have. Everybody with me? I need you guys to stay with me because we're going to be turning this into something a little more complex, okay? Stop me. And the cool thing is, so there's an imbalance in the non-responding participants that follow. And by the way, I'm only talking about AI1 right now, the red one. So you see why I'm doing the scaffolding thing? I'm like, oh, focusing on AI1. I'm just focusing on getting the mean under AI1. And this imbalance occurs by design. So we want to estimate the mean outcomes had all participants followed AI1, but not all participants followed AI1. So another way to think about it, if you guys like to think about survey design, or if you guys are causal inference people who like to think about inverse weighting, I don't care what tradition you come from, basically the responders are overrepresented. Unlike causal inference and observational studies, they don't get to say by design. You know? You know what I mean? They're in trouble. This like, oh, the sickest people got meds, you know, because they didn't do coin flips. But we did coin flips. So we purposefully overrepresented responders, or look through the other lens, we purposefully underrepresented non-responders. You guys with me? So I think you know where I'm going. This is so easy to fix because I know and I created the over and under representation. All you do is really simple. You give all the responders a weight of 2 because their little half, remember it was half? If I give them a weight of 2, right? What did I do? I doubled them, right? And then I give the non-responders, what do I do to them? What do I give them? I give them a weight of 4. I quadruple them. And now I'm back to normal, right? And I'm using 2s and 4s here, but it's equivalent if you had thought to yourself, oh, I'm just going to double the non-responders and do nothing with the responders. It's equivalent, right? I'm just scaling up or down. You guys with me? Is this cool? Do you guys think this is cool? It's pretty cool. It's like, it's a really cool little stats thing, right? And this concept is undergirding everything I'm going to talk about for the next hour. That's it. I'm just going to make it a little more like easier for you to do on a computer. That's all. That's all I'm going to do, you guys. There's nothing fancy going on here. Zero fanciness. Anyone have any questions so far? This concept is key. I'm going to get to how do you tell the computer to do this, but that's just how you hit the buttons. You got to understand why we're doing these weightings. Everybody kind of see it? You kind of see it? Yes.
Can I have a question I got about last night?
Yeah.
Danny, if I were to come up to you and say, why would I ever want to know this? Why would knowing the mean outcome under an embedded adaptive intervention matter? Why would I not just care about the responders and non-responders?
Oh, you're calling into question something more fundamental. I mean, you're calling into question this ain't.
Hypothetical Gabe is calling this into question.
Oh, yeah. Okay. A hypothetical Gabe is calling. You're calling, forget the weighting. Like, put that out of your head. You're calling into question, like, if you don't believe in this comparison, forget the weights. Just go to sleep. Go for a drink. Or, like, you're calling into question why I even want to compare these two. Well, I think it's important, right? Because, like, don't you want to know which of these two interventions, adaptive interventions, is better? That might be the kind of science question you're interested in. The other 2 questions I shared with you are not like this. So we're showing you 3 different questions. The first question was, what do I start with? The second question was, what do I do with non-responder? This one's a little groovier. You get to pick which one you like. This one's groovy. This one's like, imagine a school in which all the kids followed the red one. All right? The thing Bill Pelham advised against for like 30 years. Right? So for somebody like Bill Pelham, who's trying to champion behavioral interventions, like, this is probably exactly what they want to know, right? Or imagine a world where I start with BMOD, and if things go south, I put in the medication. This is like at the core of Bill's like career, right? I mean, that's why he designed this study, right? This is important, y'all. Because if you're the school doing your tier 1 or tier 2 programming, whatever it is, because I'm not a school person, you need to know, Like, is the school going to be encouraging meds right out of the gates, or is the school going to be encouraging BMOD? Like, what's the school psychologist going to be talking about in terms of its impact on school performance, right? That's why we need to know.
I'm convinced.
Oh, thank you. Thank you. That was a curveball. I wasn't prepared for your curveball. But do you guys see why a question like that might be important? Yeah? Any other questions? I loved it. I love that question, Gabe. Any other questions? Yeah, so Bill actually was extremely interested in this. Do you guys know the punchline? Did you guys all read the paper? Huh. Did we not include that paper in your reading list? We must have. So this paper is already published. Bill published it, or Bill published it, I don't know, 2 or 3 years ago, Billy? Maybe 4 or 5? I think it was even pre-COVID. I can't remember. Okay. In the real analysis, this one was the winner, much to Bill's content. And one of the things they realized is that when you start the kid off on med, if they become a non-responder, they're not even willing to do any BMOD because they're so accustomed to the med working. The med is working in their bodies. So it's like engagement was at the core of the why. It's like, and you see them drop like flies in the data. You see that like the kids that start off on med, they're responders, they either disappear, they attrit, they don't even bother coming to BMOD. They don't do any of the homework assignments. Whereas if you hit the ground with something a little tougher, you work on your behavior and you're struggling, and then I medicate you, well, in terms of school performance, that was better. So that's me trying to put it through my filter. But some of you here who have worked with Bill, did I do an okay job? Okay. So that's why these questions are important. And you all should read that paper. That paper is on your list. It needs to be. So this study we're showing you here has already been analyzed. And then Bill's son, also called William Pelham III or something, then he wrote the cost effectiveness analysis. And I can't remember the punchline on that. What was the punchline on that, Billy? There might have been other ones. I might be butchering it. I thought it was attendance. I thought these kids, when they became non-responders, they just didn't show up. Yeah. Right. Yeah, less rule by. And, if Bill was still with us, he would be giving that talk, right? So, but you should read it. You should read that paper. Okay. Gabe, you took me off track, but I loved it. It made me happy. It made me think of Bill, so it was good because I was trying to channel them. Okay, so back to this slide. So don't get scared. This is me trying to show the people in the room that care about this stuff how you do the weighting. Okay, how you go about doing the weighting. I think I want to ignore it, but basically you're going to go in the data and you're just literally going to take all the responders and give them a weight of 2. Everybody look at this line. Response is 0, 1. If you're a responder, means that this is 1 and this is 0, you get a weight of 2. If you're a non-responder, means this is 0 and this is 1, you get a weight of 4. That's it. You just went into the data and you gave responders a weight. Like, weighted regression? That's what I'm talking about. You create a new column. Got everybody with me? Yeah? Okay. And then the other, okay, this part's a little tricky because remember at this point in my scaffolding, I'm not showing you how to do this with all the 4 of them. So what I want you to imagine is an indicator in your data set that is whether or not you're in boxes A and B. So in other words, let's call that Z, a little indicator called Z, and it's on or off. And it's a 1 if you ended up in boxes A and B, and it's 0 otherwise. Are you guys following me? Or 1 if you ended up in boxes A and B, and -1 otherwise. You guys following me? All right, imagine that little indicator. There he is. You guys see the little indicator? Yeah? This is silly. You're not going to do this, but this is scaffolding for what's to come, okay? So you went into the data. You created a little indicator Z. Did I follow adaptive intervention 1, which just means did I fall into boxes A and B or not? Everybody with me? And you run that regression, okay? But you do it weighted. That's it. It's a weighted regression. And then if I want to know, oh, what's the mean under that intervention? Well, stick a 1 in there because 1 means you were in that intervention, and boom. So beta 0 plus beta 1 is the mean out school performance under adaptive intervention 1. There's nothing fancy going on here, you guys, but I do want you to stop me because if I lose you, I can't do the rest of this. I can't have non-responders for this scaffolding because it's going to be too hard to climb, I think. Yes, Libby.
I haven't used weights before.
Say that again?
I haven't used weights before in my work, so can you tell me, like, where does the weight, like, I see where you have the argument for weight, but, like, where does that go in the equation? Like, I'm trying to understand, like, what the weight is.
Oh, you want to, like, look at the stats under the hood?
Or you can just conceptualize. Either way is fine.
Okay.
I don't understand what the weight is.
The weight is like if you, in this very simple case, here's how I want you to think about it. In this very simplistic case, just imagine if you this is not quite what's happening, but imagine if you took everybody's school performance, their outcome, and you took the responder school performance and you bumped that up, you put a little 2 in front of it. It's actually a square root of 2, but just imagine I took the school performance for the responders and I put a little square root of 2 in front of it, and I took the school performance, the actual covariate, and I put a little square root of 4 for the non-responders, and then I just ran. Imagine if I did this regression with that new y, with a little w there. That's not quite what's happening, but I'm trying to get you some intuition. That's like weighted least squares. It's just weighted least squares. And the survey people, if you've ever done survey weights, right? I oversampled, Asian Americans, or whatever, right? I went into that community and I grabbed a bunch of them. Well, because you oversampled them, you can use the weight to undo that when you go to do the analysis, right? So you can get, this is all that's happening here. Except that the weight here is very special and unlike survey weighting because this weight is potentially impacted by whether you got BMOD or MED. That's a bit of a nuance. Survey weighters don't have quite that issue. Okay, everybody with me? All right. And actually, that brings me to why we ask for robust standard errors. So that was a good segue. Because the weights here are a function of response and non-response, meaning this weight is actually a random variable. It's not a fixed quantity. In survey weighting, typically the weights are fixed and known. They're before anything ever happened. It's not impacted by anything that the survey is trying to collect. It's not true with attrition weights, but with the over-representation weights. Well, here that's what's happening. W is a random variable. It's not a fixed number. You know what I mean? It's got a distribution, and that distribution is a function of whether I became a responder or not. Because of that, because being a responder or non-responder could have been impacted by BMOD versus MED, I can't just get typical standard errors. I have to ask for robust standard errors. Okay? So the weights depend on response status, which is unknown ahead of time. That's just a way of saying it's a random variable. And we should clarify this. The weights depend on response status, which is unknown ahead of time and potentially impacted by BMOD versus MED. That's what I should be saying. And therefore, that's why we ask for robust standard errors, okay?
It's still a variable. It still varies at random, and that's why we need robust standard errors, right? So that the source of it is not that it's impacted or not impacted by BMOD or MED. The idea is that there's a distribution here. So from sample to sample, you can have variation.
That's right.
In the rate of responders and non-responders, meaning that you would have variation.
Yeah. I know. And I was just trying to, in case anyone here was survey weighters, Billy, I was just trying to draw a contrast to survey weights where it's not a random variable. It's known because it's by design. I was just trying to do that. But you're right, Billy. So another way to explain why we need robust standard errors, which Billy just described, is because in any one data set, in this one smart that Bill happened to do, you got some constellation of responders and non-responders, but had Bill redone that smart the next year, or had there been 1,000 Bills doing the smart at the same time, every single one of the smarts would have had a different constellation of responders and non-responders. So I have to account for that sampling variability, and the way to do it, the easiest way to do it, there's many ways to do it, You go to Bootstrap. There's 100 gazillion ways to do it, right, Gabe? The easiest way to do it is robust standard errors. It's in all your packages. Okay, so all I've done so far is teach you how to get the mean under one adaptive intervention. Oh, and if you did this, and you will on the virtual days, this is what you get. 2.66. I shouldn't be showing that p-value because there's no comparison here, right? This is just the mean under AI1. Ignore that p-value. I want to get rid of it. And there's the standard error. Okay? And this is what the output, the regression output looked like. This is just when I did 2 times this, which is that. Or so, this is this plus 2 times this. There it is. Everybody see that? Oh, anybody know what the negative tells you? Oh, let's see if anyone can figure that out. What does the negative tell you? Do you guys remember what Z was? Z is on if you followed AI2. What does that little negative tell you? Anybody? That if I compare, well, Z is on if you followed AI number 2, adaptive intervention number 2, right? And then if you didn't follow AI, that means you followed one of the other 3, right? So this little negative is telling you that compared to the other 3, AI2 is lesser than, right? It's kind of telling us, like, it's not that interesting. You would never put this in a paper. You would never do a smart for this. But I'm trying to get you guys to get intuition, right? This is the causal effect of following AI2 versus not. So it turns out following AI2 has got a little ding on its side as compared to the other 3 adaptive interventions. More to come, more to come. But you guys following me? Are you getting the intuition? Yes? Is it fun? Is it fun? All right. All right. Yeah? It's fun. It really is. Okay. All right. So we know how to account for the imbalance in non-responders following AI1. And we could just redo that for all 4 of them. But the problem is that it's not really satisfying to run 4 different regressions, and every single time, all you get is the mean outcome. You know, I could do this 4 times, and I get the mean outcome under AI1, the mean outcome under AI2. But that's not what the AIM type 3 is. What's AIM type 3? It's the comparison, right? So what do we do? What do we do? Are you guys ready for it? Here's what we do. So that was scaffolding 1. I'm ready to go to scaffolding 2, and then we're going to hit the home run at the next, I don't know if it's the next module or at the end of this. Is everybody with me on scaffolding number 1? All right, let's go to scaffolding number 2. Scaffolding number 2 is I'm going to say, okay, I want to do in one fell swoop AI number 2 and AI number 1. So you see that 2.6 from one regression, and the 3.83 from the other regression for AI2. So obviously AI2 is kicking butt, right? Right? How do I do those 2 at the same time? All right. So there they are. There's the red one. There's the blue one. And why am I doing this? Because this is my primary aim, right? I want to do this in one regression. I don't want to run 2 regressions. And either way, if I run the 2 regressions, I still can't get my answer. Well, you could get the answer. You could do 3.83 minus 2.66, but then you have no idea what the p-value of the standard error is, right? So that's not useful. All right, so let's do it. How do we do this? Easy peasy. All you do is create one indicator, right, for whether or not the person is consistent with A1. Create another indicator for whether or not the person is consistent with A2. Great. Do your weighting, right? And then throw away everybody else. Throw away all the kiddos consistent with adaptive interventions 3 and 4 because it's not, you don't even care about it. That's all I'm doing here is I'm saying, hey, throw away everyone unless you're part of adaptive intervention 1 or adaptive intervention 2. Has everybody seen what I'm doing? I just threw everybody away, kicked them up to the curb. You guys with me? But now in my data set, all I have are people consistent with AI1 and people consistent with AI2. So I could actually go back to Z1 because now Z1 in this new data set is actually telling me whether you're an AI1 or AI2, right? Because I kicked everyone else out. You guys see that? Yes? And then that's it. That's what I do. I do my good old trusty regression. And we already discussed earlier that 2 times beta 1 is the causal effect of following AI1 versus following AI2. So let's see. Oh, so now I have this new line. Finally, finally the line I care about. There's the mean under AI1, there's the mean under AI2, and now take the difference. It's just 2 times that parameter. Yeah? Are we happy? All right, let's look at the results. Thank the Lord that when I did the regression in 1 time, rather than 2 regressions, I get the same answers, and there's the difference. But this time I got myself a standard error. Yay! I can do inference. I can tell my readers in my paper what the p-value is, right? Is that cool or what? It's cool. Oh, by the way, the p-value is significant. Now you're throwing a party because you just got tenured, right? Oh, I hate that so much. You should get tenured whether or not you get a p-value. We need to change that fast. Okay. All right, everybody cool so far? Yes? Okay. Well, it turns out that you can take this to the limit now. Now that you guys know how to do this, right, which is essentially just running this regression, now do everything you guys know how to do. Throw some covariates in there. For efficiency or for, right, you were asking me earlier, what if I had imbalance and you're worried about it and you pre-specified your x's? Throw them in there. Baseline oppositional defiant disorder, the kid's race, whatever you want, right? Throw it all in there. Whatever you thought was associated with y, which you pre-specified, throw it all in there. And you could do that. And it's not complicated. So here I am throwing in whether the kid has oppositional defiant disorder. I mean-centered it just so that I can ignore that. Right? Because that's not part of my science. The association of whether the kid had oppositional defiant disorder with school performance is not part of the purpose of, it's not the primary aim of the science. So I want to throw it in to get some statistical efficiency, but I'm just kind of ignoring it. Right? And so when I do that, now the estimates change a little bit. Of course they did, because now I'm adjusting for an x. But I want you to notice something. When I didn't adjust for x, what was my standard error? Can somebody say it out loud? Point what? 0.3, that was the standard error. Well, consistent with good practice, and you guys have some really good people in your education space, like Elizabeth Stewart, Tipton, Larry Hedges, all those people. They write these beautiful papers, right? Bloom. They write these beautiful papers on the power of adjusting for covariates and all that. Well, I expect that when I throw that covariate in there, this standard error gets smaller. So let's see, did it? Hooray! It did. That tells me that oppositional defiant disorder was correlated with school performance, thankfully. And it wasn't very strongly correlated, but hey, I got my efficiency. It's all good. You pre-specified it, and I'm still getting a significant, well, good, which you would expect, right? Because I got it to be significant here with a very noisy estimate. Well, I have an even better estimate. It's more precise. I'm still significant. Yay, everybody's happy. Any questions so far? Yes? So now you got tenured and you have more certainty. No, I'm joking. I'm joking. You guys know I'm joking, right? I refuse to accept that people get tenured based on whether the CP values.
If I want to compare 3 of the embedded designs, it's just another indicator, so my regression will have 2 indicators.
I'm going to show you something even better. So this is, so you're rushing me, which is good. Should I go faster? Ian, how much time do I got for this one? Should I go faster? Oh, so, okay. I got time. All right. So, so use a weighted and replicated least squares regression approach equipped to address aim types 1, 2, and 3. So I'm about to show you the punchline. You're not going to do either one of the things I just taught you. You're going to do this next thing. But I had to show you these 2 things so that you understand the next thing. All right. So I want in one regression to be able to get all 4 of the means. I want to compare AI1 versus AI2 versus AI3 versus all in one fell swoop. And I'm just going to show you how to do it. It's so cool. It's groovy. Okay? This next thing I'm showing you is what you're going to do in your analysis. Notice something interesting about this. There's a little something I need to share with you. It turns out when I do it all in one fell swoop, there's a little thing, a little barrier I have to overcome. The barrier is this weird fact that AI1 and AI3 share responders. And it cannot be ignored. You have to do something about that. That's why I had to do all the scaffolding, because now I want to bring your attention to that concept. Do you guys see that? So it turns out that responders to med are actually part of two different interventions. Of course they are. These guys are part of the AB intervention, and they're part of the AC intervention, right? Yeah? So I got to address that and the stats. But it's really easy. You'll see. And it happens again at the bottom of the design. AI2 and 4 share responders as well. Okay? So I got to do something about this or else things are not going to go well. Okay? But it's really easy. So what's going on? In the ADHD SMART, all responders are consistent with two adaptive interventions. Responders to MED are consistent with A1, A3. Responders to BMOD are consistent with A2, A4. So if our goal is to estimate the mean outcome under all of them in one fell swoop, I must share the responders somehow, right? I got to share the love. Yeah? But how? So what we do is there's a little trick, and this is not, the trick I'm showing you here is not the statistics. It's how we fool the computer to do the statistics. Okay, you guys? I need you all to realize that. Like, I'm not doing some magic here. Magic statistic. Like, the statistics are good. They're proper. They're phenomenal. They're perfect. This is, what I'm about to show you is how I fooled a computer that does SPSS and STATA and whatever to do the statistics, because it turns out that when we developed the method, Billy, Susan, and I, there is no computer program in the world that could do what we're about to show you, or the statistics that's underlying this. So I'm not showing you the stats. I'm showing you the thing we did to fool the computer. Is everybody with me? And let me show you what we did. We tricked the software into doing the following. So all we do is we replicate responders. So we literally are going to share the love. We're going to create every single responder. I'm going to go into the data, and I'm going to create two responders. So if Danny was a responder, or Luis was a responder, I'm going to make two Luises. But here's what's cool, is I'm going to say to one Luis, hey, Luis number 1, just pretend you're part of adaptive intervention number 1. And I'm going to say to the second row, Luis number 2, just pretend you're part of adaptive intervention number 2. So I'm going to assign one Luis a 1, and I'm going to assign the other Luis a -1. Let me ask you guys something. Do you remember that when we first showed you the data in a SMART, do you remember that responders had a what in the A2 column? What did they have in the A2 column? Missing. Well, I'm tricking the computer into thinking there's two Luises now, and I'm going to fill in that missing value. One gets a 1, one gets a -1. It's not wrong. That is what sharing the responders means. And I'll show you why it's not double dipping either. Okay? I'll show you why it's not double dipping. Because what I'm going to do is I'm going to do that. I'm going to copy Luis twice. I'm going to fill in their A2 column with a 1 and a -1. And then I'm going to tell the computer, dear computer, please don't treat the two Luises as different people. I'm going to tell the computer it's just one Luis, so that my standard errors are correct. Everybody got it? Not unlike when you tell the computer, all of these kids were in the same classroom. Don't treat them as independent. Just like that. Just like that. No difference. You guys see this? So this is why when Billy started working in this area, and Billy was spearheading these seminal papers in psych methods. This is why we started using the phrase, we're using a weighted and replicated regression. Because it's not just weighted, it's also replicated. So if you start reading our papers, you'll see us use that terminology. We don't always use it. Sometimes we just say weighted, but sometimes you'll see us use the term weighted and replicated. But now you know why. Okay? There's the weighting and replicating. They serve different purposes. This is just a review. Weighting accounts for the over-under representation, which I created. Replicating allows us to use standard software to do simultaneous estimation of all four. All right, so in SAS, this is how you replicate. I don't know what software you guys use, but it doesn't matter, right? You just say, oh, take everybody who was a responder and make 2 of them. Take everybody who was a non-responder and just keep the one dude. All right, yeah? And then, oh, by the way, that's the replicating part. By the way, give all the responders a weight of 2 and give the non-responders a weight of 4. Easy peasy, lemon squeezy, right? All right, here's what it looks like in the data. So these guys in red are responders. This guy 53 is a non-responder, right? When I did my whole oh, and there's the weights, right? When I did the replicating, well, where is it? Wait a minute, something went wrong here, you guys. Oh yeah, there it is. This is Luis and this is Luis. I looked at this and I shouldn't have. This is, yeah, I got confused. There's Luis and there's Luis. And look, oh my God, Luis doesn't have an NA anymore. Right? That's it. So there's my weight, there's my replication. And now you go run this regression. What is this regression? A1 is an indicator of whether at stage 1, that's why it has a little 1, I got B mod versus med. A2 is an indicator of whether in stage 2, that's why there's a little 2, I got augmented versus intensified. Beta 3 is the interaction term. We haven't talked much about the interaction term, but it's a pretty important, beautiful thing. Because in the ideal world, you would expect to find that in one direction or in the other, that these two things I did at different stages came together to really blow up school performance, right? Right? You want a positive synergistic interaction between what you did in stage 1 and what you did in stage 2. That's why I'm putting that term in there. The other way, for those of you that are like me, that I always have to go back to low-level thinking. The reason there's 4 parameters is because there's 4 adaptive interventions. Right? That's how I think. Right? Right? I'm getting my 4 means out of this regression. Beta 0 is just the overall mean school performance. It's just average school performance. Averaging over all treatments. It's like, take everybody in your study and just tell me what the average school performance is, beta 0. 2 times beta 1 is the main effect of B mod versus med. That is aim type 1. 2 times beta 2 is the main effect of augment versus intensify among non-responders, which is aim type 2. And then if I wanted to get any pairwise combination I want among the 4, I just play around with the, sticking in 1s and negative 1s, right? So and here I'm doing it, right? So I can get each mean, right? Because I stick in the appropriate number, a 1 from B mod, a negative 1 from med, right? I can get all my 4 means, and then I can even do my differences. The difference between AI1 and AI2 is that thing, right? It's a little complicated, but it's no big deal. I mean, it's not a big deal. And in fact, there's a lot of intuition here, because there's a lot of intuition. That's why this paper is so highly cited. So, I can't block it. So can you guys just focus on negative 2 beta 1? What was that again? What is 2 beta 1? Main effect of first stage. And wasn't AI1 and AI2, weren't they only different in terms of first stage? Right? So I would expect that term to be in there, right? But there's something else going on. There's the, what term? I'm picking up the interaction term. Yeah, so it's got a lot of intuition. If there was no interaction, back to you. If there was no interaction, if the interaction is 0, what is the difference between these two? The same as the main effect of stage 1. Back to this. You guys see that? Both effects are valid. Both are causal. You get to decide which question you're most interested in. Isn't that groovy? Oh, I love it so much. All right, and I lost my little thing somewhere along the way. Anybody see it? This is my own. Okay. All right. And then ProgGenMod is so straightforward. There's my little regression. Put the main effect of stage 1, put the main effect of stage 2, put the interaction term, do my weighting, boom, 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 boom. And of course, I can get all 6 pairwise comparisons, but I only show you 3 there because I'm running out of room in this slide. Okay? So in one regression, you get everything you need. Isn't that amazing? So freaking groovy. All right. Note, We get exact same results as before when we compare to A1, AI2, but now we can simultaneously make inferences. So what you should be seeing is that this negative 1.16 is what we got earlier. All right, but wait, there's more. It's like a commercial, right? Weighted and replicated, there's one more thing it allows you to do. I can put covariates. So I can do everything you wanted to do earlier. You know, if I anticipated oppositional defined disorder being highly associated with school performance, when I pre-specified my analysis in the grant, I would have adjusted for oppositional defined disorder. But guys, what is the most important? What? Can I ask you guys something? My goal is to improve school performance at the end of the year. What covariate at baseline is most associated with school performance at the end of the year? School performance at the beginning of the year. So please adjust for that one. That's going to eat up a gazillion amount of your variance, right? I mean, you guys, Steve Rodenbush and you guys taught me that, right? All these hierarchical linear models and the within-person correlation. Mason, you're going to tell me I did something wrong.
No,
oh.
Not softball, but why can't I want to adjust for adherence. That seems like it might be strongly correlated with end-of-study school.
You want to adjust for adherence?
Yeah.
You will have committed to the hardcore trialists, you know, the guys that publish in the journal Clinical Trials. You have committed the biggest sin of your life. This is in the olden days. This shows you how old I am. I was trained, thou shall never adjust for a post-randomization covariate. You know, it's the way I was taught. Thou shall never. Please don't you dare throw in anything other than baseline covariates in here. Why? Well, because adherence is impacted by what, y'all? Potentially impacted by A1. So please don't do that. That's the same reason we don't throw response, non-response in this regression. Please don't do that. You will just slit your throat. You'll never get it published. If you do get it published, that tells you something about that journal. You know what I mean? Some sketchy stuff going on there, okay? So, okay, let's go back to, so you're only gonna wanna put baseline covariates. Adjusting for baseline covariates that are associated with the outcome leads to more efficiency. You guys know that. Bloom, Rodenbush, all your people, Tipton, all these guys have been saying that for 15 years, right? Ever since IES was founded, they've been saying that, right? And that's what should happen here too. So, and I don't know if it's gonna happen in the fake data. So my standard error was what? 0.323, okay. So let's see. Yeah, awesome. There it is, 0.222. So I am indeed getting a more certain estimate of the causal effect. Yay, as it should. Oh, this is interesting. And that's it. Okay. What do you guys think? How many minutes, wait, before Sam, how many minutes do I have?
You have actually, is this right? 35.
Let's take a bunch of questions. No, this is terrific. Let's take a bunch of questions, and then maybe we'll use some of that 35 minutes to do more small group work.
Good idea.
I know. All right, so let's take some questions. What do you guys want to throw at me? Fernando.
What's your question? Like, because your outcome in this case is academic performance.
At the end of the school year.
At the end of the school year, but probably you will have children nested in schools.
You'll have to what?
Children that are nested in schools, potentially, right?
Oh, potentially.
So,
but the children were randomized in this study, so it doesn't bother me. But
the question is that, so some reviewers may tell you, like, how do you adjust like the composition of variance between within schools and between schools, right? But I think that might.
You mean imagine a world? I think what you're saying is, Danny, and I don't know how Bill did this. I don't know if he did it at one school or many schools. I actually don't remember. But you're saying, Danny, imagine if this child level SMART was done at like 16 schools. That's what you're.
Yeah, exactly.
Okay, let's pretend that that's true.
So that depends how you randomize, I guess, right? Because you can.
You don't randomize the schools. This is
You're randomizing kids.
No, this is not. Yeah, so let's all back up. The Pelham SMART was not school randomized. We're not talking about interventions for the school. We're talking about interventions for the kid. So the Pelham study randomized kids.
Yeah, but I understand that. But where I'm going is that your outcome is it's clustered within the schools.
Yeah.
Right? So you have some variation
You could.
between the schools.
You could. And if you wanted to soak that up, by all means, throw it in there.
Okay.
You could throw it in as a covariate. You can use whatever clustering hierarchical models you like. You can put it into the variance component. Like however it is you want to do it, do it.
Okay. But the procedure that you show in replicating and the weighting has to be there.
Yeah.
Yeah.
Yeah, it has to be there. If you're going to use this method. There's other methods to analyze smart data, but we only have one day today for stats. So there's other methods. So Mason, my student Mason, is working on a method where you actually do adjust for responder status, but you have to be really careful, or else thou shalt get your throat cut off by the trialist. So there are ways to adjust for like post-randomization things, but you gotta be real careful. So that's why we don't even teach that one. Like we wanted to teach an analysis that was so familiar to you that you're just nodding your head the whole time. And also familiar to your hardcore trialists who wouldn't ever dare adjust for a post-baseline covariate. And that's what we presented to you today.
So in function, when you ran the final full version where you're testing all effects simultaneously, you're both weighting and replicating?
Correct. I have to share those responders.
So is what's actually happening, is each respondent given a weight? So those respondents are actually included in all comparisons, or are they dropped out of the contrast?
I know how to answer your question. I think I already know where you're going. So, and this is going to be an intuitive answer because I'm not showing you the math, but I can. When I don't have any covariates, they are getting dropped out. It's like, it's pure, if you will. The moment I throw in a covariate, I'm pulling across everybody, right? Because that's what the covariate does, unless the covariate is binary. But typically they're continuous school performance. So once I throw the covariate in there, I pull across, and that's why, I don't know if you guys noticed this, that's why when I showed you these results, let's see if I can replicate what I'm trying to say. That's why when I showed you this result, it was identical to the two scaffolding sections, like identical to the whatever decimal your little heart desires, because this analysis here didn't have any covariates. It was pure, if you will. So you're going to get exactly the same mean if you had done separate regressions versus this full. But the power of this approach is, in fact, in being able to put covariates. Because, like, think about it. If Susan Murphy, Billy, and I had developed a method where you guys were telling you, no, don't put any covariates in, are any of you guys going to pay attention to us? No, you wouldn't even read our paper. So everybody I know, domain scientists like you guys want to put covariates in, and so there it is. This is how you can do it. This is how you can trick a computer to do it. Are we good? Oh, Sam.
I appreciate this is niche, but so we would typically adjust for stratification factors. So
Yeah, you better believe it.
If you're comparing embedded adaptive interventions against one another, and you've got different stratification factors for your second randomization as you did your first.
You can't adjust for them.
You can't, right? Okay.
But I can show you how.
Because it's a post-randomization.
Yeah, can I show you how? Okay, this is not part of today's topic. This is an advanced topic.
Can you repeat his question?
Oh, yeah, let me repeat the question. It's a very, very, very intuitive question that I love so much. I'm trying to find a picture of the smart. Okay, remember the module that's missing that we need to create for next year, which is like, oh, don't forget to stratify your randomizations. Remember that? Right? So, like, chances are that, and I don't know what Bill did. I just have no idea. But chances are Bill stratified this coin flip, maybe on some school performance cutoff, or maybe on like ODD diagnosis, whatever. There must have been some stratification, right? So this wasn't just one coin. This was like many different little coins under different subgroups. So like all the oppositional defiant kids got a coin. Everybody got coins? Okay. But also, and I don't know what Bill did, but I'm telling you guys what you can do. These two can be stratified. Like if it were me, I would probably, in fact, I always stratify on like school performance at the time right before the coin flip, because it's always repeated measures that we collect, right? Right? Like, I know that today I'm only showing you a Y at the end, but in reality, we always collect longitudinal outcomes, right? Rod and bush. Okay, so I have like a Y here. So I'll always put a cutoff on that one and make sure that this coin flip, right? Because the last thing I want is for the kids that were really high performing by fluke, they're the ones that got augment, and then everybody's complaining that my trial failed, right? So all of you guys are going to do the same thing. All of you guys are going to be stratifying, right? So now Sam's question. Sam's question is like, wait a minute, Danny. So great. Thank you so much, Danny, for this regression. We love it, Danny. You get to adjust for your stratification variables, but Danny, how do I adjust for the stratification variables for that second randomization? You just told me I can't, or I get my throat slit, right? That's Sam's question. Everybody got his question? Okay, it turns out, and this is really cool. This is in our stats papers, but not our modules, right? Because this is like Smart 101 for y'all. So we actually, this is going to sound bananas, but you can put your stratification variables in the weight. And if you want to learn how, Tim, tell us all about your paper.
Yeah, we have a paper in depth that looks at ways to soak up that additional variance through the weights and other strategies.
Tell them the journal, because they're all going to love that you published in there.
Journal for educational and behavioral statistics.
Yeah, JEBS. So Tim just finished getting a paper accepted there where he shows you how to do that. If you really wanted to sort of adjust for post A1 variables, there's a way to fold them into the weights. So it's in there getting adjusted for statistically. It's just not in there in the way you and I are accustomed to seeing it, because the way you and I are accustomed to seeing it harkens back to 2-arm randomized trials, but this is not a 2-arm randomized trial. So, yeah, Mason.
Follow-up, let's say our randomization, we weren't quite 50-50 split.
Oh, yeah. 48-52.
48-52.
Uh-huh.
Should we use our design weights? Or should we maybe use the observed distribution of weights?
Okay. Yeah, that's a great question. So what Mason is saying is, Mason is drawing this cool connection that I want y'all to make as well, that, oh, Danny, the reason you chose a weight of 2 and 4 was because you designed the study with a half and a half. But Danny, in the actual data, when the data showed up on my doorstep, I may not have had exactly 50% of the kids in augment and 50% in intensify. I might have had 58% and 52, right? Because nothing is perfect, right? Right? Unless you have a gazillion sample size, which none of the people in this room have, except maybe Greg. I'm always it's remarkable how you guys can find students, man. I don't know how you do it, Greg. I don't know how you do it. It's remarkable. But the rest of us poor people that don't have the ability to recruit hundreds and thousands of kiddos, we rarely will get a 50-50 split. We'll get like a 48-52. So that was Mason's question is, do I still use a 2 and a 4 when in fact the data is showing me a 48 and a 52? It turns out, y'all, that instead of using 2 and 4, you can use what Tim in that JEBS paper calls the empirical weight. So instead of 1 over a half, which gives you the 2, and 1 over a quarter, which gives you the 4, you just do 1 over 48%, which gives you something a little different from 2, and you use 1 over 0.28. You know what I mean? And it turns out, so we call that the empirical weight because it's a 2 and a 4, but it's like tweaked a little because in my data it wasn't exactly 50-50. It turns out that if you do that in this weight, guess what, y'all? You actually get more efficiency just doing that alone. In other words, it's a cool little fact. It's provable that you get more statistical efficiency. You get a smaller standard errors. You get a better chance for a p-value that's smaller, if you will, if you use the empirical weights. The catch to all this is if you're like Greg Roberts, it's not going to matter because Greg is going to hit his 50-50 no matter what, or it's going to be like 0.4499999. You know what I mean? Because he's got a gazillion kids recruited. So this helps a lot of us who need a little bump in efficiency just resulting from the fact that I only had 112 kids or whatever. You know what I mean? Does that help? It's so cool. Stats is cool, isn't it? And then Sam, to your point, empirical weights gives us a good efficiency. And then if you throw the stratification variables in there, if those stratification variables are in fact correlated with school performance, you get another bump. But Tim, tell me about that. What did we find in our paper? The bump was not too big, or can you remind me? What did we find? It's a small bump. In other words, you get a big bump in efficiency from using the 0.48 and the 0.52, and then the next bump you get from including the stratification variables is not as big. But all of these are tricks. The catch is, y'all, you got to pre-specify all this. You can't go fishing, right? So you got to tell the reader, when you write the protocol paper, you got to tell, I'm going to be using the empirical weights. These are the covariates I'm adjusting for. You can't go off like figuring this out when you get the data. That's the catch. Or else no one believes your p-value. Yes, you.
I have a question about the replicating and weighting. I feel that like one intuition to understand weighting is actually replicating. It's if someone has a weight of 4, it's like we replicate this person 4 times. We adjust that in the standard error, but that's the intuition for getting the weight estimate. So I was trying to think how to reconcile this intuition with the actual replicating that you're doing for the responder.
Yeah, what a great question. Essentially, Shiyu's question, which is really insightful, is essentially this idea that like, isn't replicating just a different kind of weighting? And guess what, y'all? It is. They're both weightings, but because they have these different flavors and because we wanted to teach y'all how to go do the trick on the computer, we gave them different labels. You know what I mean? But when you look under the hood and you look at the math, you will see that the replicating and the weighting are all right there staring at you. In fact, some people stick the some people stick the replicating in the weights. But I'm not doing math today. I'm showing you how to trick a computer. So we have weighting and replicating. But I can show you later. I can show you.
I have another question about the coding. So the way you code it is that for responders, the A2 is you assigned 1 and -1.
Right. Because I wanted to tell the computer, I need 2 Luises, one that's with AI1 and one's with AI2.
I think I saw some example that you assign responder with 0, that I saw there's some paper that's coded like that. Does that make a difference?
I don't know. If you're doing that, you wouldn't be trying to trick SAS. Yeah, it just means that you're using some other trick. You know what I mean? But if you did that here, you'd get a mistake. Like if you were trying to use this trick, you'd get a mistake. Remember, I'm not showing you stats right now. I'm showing you how to trick a computer to do stats. Because the computers don't know how to do analysis of smarts, because smarts are brand new. But actually, where's Wen Chu? He's not here. One of my other students who is developing methods for clustered smarts, he's just completely bypassing trying to trick a computer. He's like, forget about it. I'm just going to write the code from scratch. So like when his paper comes out, you will have to use his code for what it's worth, just because it got a little hairy. It turns out it gets a little hairy when you get to clustered smarts, and even sometimes repeated measure smarts, it gets a little hairy to try to do the trick we're talking about here. Still doable, but it's just, I don't even know if it's worth the time. I feel like I'm getting an echo. Is everybody good? Does everybody have fun? I think we should stop and get a rest or something. What's next on the agenda?
Next is small group work at 2:30.
Oh, why don't we give folks a break?
Yeah, 10-minute break.
Yeah, how about everybody comes back at 2:20? Or 2, is that good?
Yeah.
Yeah?
Or 2:30.
What? 2:30 is fine.
So 20 minutes break.
Great. Why doesn't everybody go outside? You got till 2:30. Everybody got it? Clap it out for yourselves. That was heavy duty, right? But you did it.